We'll study angular SHM. Yes, angular simple harmonic motion. Let us consider a small disk of mass m is hanged with the help of light inextensible string. Now, if we twist this disk and without moving it a lot, keeping it in a vertical position itself, if we release the disk, then we see that the disk starts performing a rotational motion. So whatever the twist is there in the string, it unwinds, and so because of that the disk starts rotating. But when the string is completely unwound, the disk keep on rotating, and so the twist is set into the string in opposite direction. And then the rotational motion goes on decreasing, the disk stops rotating, and then again it starts rotating in opposite direction. And so in this way, the disk will rotate in clockwise manner and in anti-clockwise manner. And this will keep on repeating again and again. And so in this way, this will set into a motion which is called as angular simple harmonic motion. Now in this case, when the disk is rotating, it experiences a torque tau. This torque is directly proportional to the twist in the string theta. The string will get twisted, and so the torque experienced by the disk is directly proportional to the twist in the string. This torque is called as a restoring torque. Just because as the twist goes on increasing, the torque goes on increasing, but the restoring torque is in opposite direction to the angular twist in the string. And so if you give the equality sign over here, it becomes minus c into theta, where c is the constant of proportionality. Negative sign indicates that the restoring torque and the angular twist are in opposite direction. C is called as constant of proportionality. It is torque per unit twist. Torque per unit twist. Yes. We know that in rotational motion, torque is equal to I into alpha, where I is the moment of inertia of the disk, alpha is its angular acceleration. And so if you substitute this value over here, I into alpha is equal to minus c into theta. Therefore, alpha will be equal to minus c upon I into theta. Moment of inertia of the given disk is constant, so c upon I is constant. So alpha is directly proportional to theta. Angular acceleration in angular SHM is directly proportional to the angular displacement. Angular acceleration and angular displacement are in opposite direction because of the negative sign. And so in this way we can show that the rotating disc and with the help of a string from a rigid support performs angular SHM. Now in this case, if you want to find out the period of the rotating disc, angular pendulum, the period of the angular SHM will be 2 pi upon under root angular acceleration per unit angular displacement. So period of angular SHM is T is equal to 2 pi upon root of angular acceleration per unit angular displacement. Now let us find the relationship for vibrating magnet in external magnetic field. Consider a bar magnet be placed in an external magnetic field of induction B. So this is the magnetic field of magnetic induction B. So this is a bar magnet, gets aligned in the direction parallel to the magnetic induction. If it displaces this magnet by small angle, say theta, then on this magnet a restoring force acts. The restoring force acting on the magnet will be given by magnetic dipole moment into magnetic induction. The force forms a couple and separated by a perpendicular distance. Here theta is the angle, so over here angle will be theta. And so force into moment arm is the torque. And so we can say that here on this particular bar magnet a restoring torque acts, which takes the bar magnet to its original position, but due to the acceleration as it has gained, it crosses and it goes to the other side. Again the restoring torque acts on it, and so the bar magnet keeps on oscillating in magnetic field. So here the restoring torque is given as minus NB sine of theta. This is the perpendicular distance as we find between the two forces acting, and so it is sine of theta is opposite side upon hypotenuse. And so here we can say that torque is equal to minus NB sine of theta, as theta is very small, sine of theta is approximately equal to theta. So restoring torque is minus NB theta. minus sign indicates that the restoring torque is opposite to the angular displacement theta. We know that torque is I into alpha, this is equal to minus mb theta. So alpha, that is the angular acceleration, will be minus mb upon I into theta. Yes. To avoid the confusion of m for the mass, in the textbook this has also been denoted as mu. And so angular acceleration alpha is equal to constant into theta. Minus sign indicates alpha and theta are in opposite direction. In terms of the magnitude, it is mb upon I into theta. So alpha upon theta, this is angular acceleration per unit angular displacement. This will be equal to mb upon I. So m is the magnetic dipole moment, b is the magnetic induction, and I is the moment of inertia of the bar magnet. From this we can find out the period of oscillating bar magnet in uniform magnetic field of induction B. T will be equal to 2 pi upon under root m b upon I. So period is 2 pi root of I upon mb. So knowing the moment of inertia of bar magnet, magnetic dipole moment and the magnetic induction, we are able to find out the period of oscillating bar magnet in external magnetic field. Frequency with which the bar magnet oscillates is eta is equal to 1 upon t. So this will be 1 upon 2 pi under root mb upon I. And so in this way we are able to find out the period and frequency of the angular simple harmonic motion. And so the definition of angular simple harmonic motion is given as the oscillatory motion of a body in which the torque for angular acceleration is directly proportional to the angular displacement and its direction is opposite to that of angular displacement. Hereafter, in the textbook, we are having the two units, that is the damped oscillation and the free oscillations and the forced oscillations, and the concept of resonance. So this has now become non-evaluative, and so we will just have a small discussion and a mention about what the damped oscillation, free oscillation, forced oscillation and resonance is. Damped oscillations. Yes. So if we have a spring, and to this spring if we attach the mass, make this mass to perform simple harmonic motion, if K is the spring constant, the mass moves up and down performing simple harmonic motion. In this case, is equal to minus kx, where x will be the displacement of the mass from the mean position either in the upper direction or the lower direction, where k will be the force constant, or it is also called as the spring constant. This is the normal oscillations going on. Now if we modify this a little to this, suppose if we fix up a vane and this has been immersed in a solution of certain viscosity, there, and if we allow this now to oscillate, as the system, as it moves up and down, the vane moves excuse me, in the liquid of certain viscosity, the liquid exerts the force on the vane, which prevents the free oscillations of the spring and the mass, and such oscillations are called as the damped oscillations. Now here we consider this force acting on the body without the damping solution as Fs. Force acting on the system when we are having this immersed in the liquid Fd, and this force is called as a damping force. This damping force is given as minus V into V, where force is in opposite direction to the velocity with which this vane moves up and down. Negative sign indicates that they are in opposite direction. B is the constant of proportionality. And so the total force experienced by the system F is equal to Fs plus Fd. Now as we know, F will be equal to minus Kx minus Bv. V is the velocity, x is the displacement. But what is the force? Force is mass into acceleration. So m into acceleration, this will be equal to minus Bv minus Kx. I have rearranged the term, velocity term I have taken first. But how we are able to express the acceleration? We can express the acceleration as the second order derivative of displacement. Velocity is dx upon dt minus kx. K is the spring constant. And so when we write this as m d2x upon dt2 plus dx upon dt plus kx, this is equal to 0. This is the differential equation for the damped oscillations. So in this system we have a spring of certain spring constant k. Here is the mass attached to it. Mass is m, to which a vane has been attached, which has been immersed in certain liquid of certain viscosity, and when the oscillations goes on, these oscillations are given by the differential equation m d2x upon dt2 plus v dx upon dt plus kx is equal to 0. This is the second order differential equation having the two constant